So thanks, Mark, for having me here. Thanks, everyone, for coming. We're going to talk about efficient empirical revenue maximization. But before we talk about empirical revenue maximization, let's talk about Bayesian revenue maximization. Bayesian auction, sometimes called Bayesian mechanism design. I'm going to use the words auction and mechanism to mean the same thing in this talk, so please forgive me if I'm not completely consistent. So Bayesian auction design is a commonly used framework for capturing the auctioneer's partial knowledge regarding the buyers. So we have a single seller, maybe many buyers. So maybe I'm the seller and maybe I'd like to auction off this clicker. No offense, get a new one. And my goal is to maximize my revenue. So had I known that this clicker is worth $5 to Avishai, then I would have said $4.99, take it or leave it. And since by saying it's worth $5, I mean that Avishai would pay any price up to $5 for it. So if I say $4.99, take it or leave it, Avishai is going to say take it. He's gaining a cent by that somehow, and that's obviously the best I can do. Now the problem is, what happens if I don't know how much it's worth to Avishai? Maybe I don't know that it's worth $5 to him. Maybe I know that it's worth something between $3 and $7, say uniformly. So if I say $5, take it or leave it, I might make $5, but maybe it's worth less than $5, and then I don't make any money off it. If I lower the price, the chances of selling are higher, but the revenue is lower when selling. So the goal in Bayesian auction design, the Bayesian comes from the distribution that we have on the willingness to pay for the clicker for every buyer that we have. So in the setting, the auction designer is given a distribution for each buyer. You can think about these as a product distribution, so the buyers are independent. And the goal is to find a truthful auction. We're going to get to the meaning of the word truthful soon. To find an auction that maximizes the revenue to the auctioneer in expectation over the given distributions. So in the case of just Avishai, from $3 to $7, I can write the expression for the revenue for each possible price, derive and find the maximum. That's if I want to post a price. But if there's more than one bidder, there are more elaborate mechanisms than just posting a price. We can do randomization, we can sell lottery tickets, we can have them fight against each other for the highest bidder, etc., etc. But we need to have it truthful. Truthful means that I am going to ask each of them how much is this worth to them, but they can lie. So for example, the mechanism of asking the buyer, how much is this worth to you? And then, depending on the response, saying 1 cent less, take it or leave it, that's not truthful because he's going to say 1 cent, even if it's worth to him $10. Also, we assume truthful means both that and the fact that we always assume that the buyer has an option not to participate. So saying you must buy this for $1 million is not truthful, because the buyer can always say, give me nothing, take nothing from me. So under these two constraints of truthfulness, that both comprise truthfulness, the goal is to find an auction that maximizes the revenue in expectation over the given distribution. So there's a distribution, we get it, we do some computations on it, we output an auction, and the auction should be good for the distribution in the sense of maximizing our revenue. Now, usually, this is the classical framework that economists have been using for years, and computer scientists as well recently. But the question always is, okay, so how does this represent reality? How do we get this distribution? And people always wave hands and say something like, maybe you know the market very well, you've seen transactions in the past, you've observed transactions, you did market surveys, I don't know what, and so you know the distribution quite well. So that's nice, but a few years ago, a new line of papers emerged, and they said, well, if indeed that's your story, that you've observed past transactions and did market surveys, etc., then you don't really know the distribution. You know many samples from the distribution. So to make it more realistic, there's a distribution. You take polynomially many samples. That's what happens when CS people enter econ fields. They start to say things like polynomially many. So there's distribution. You get polynomially many samples from the distribution. Do whichever computations you'd like on them. Output a truthful auction. And this truthful auction should approximately maximize revenue in expectation over the distribution that you don't know, that you've only seen samples from. So this is what's called empirical auction design versus Bayesian auction design. Now, when I say that this auction should maximize revenue over this distribution, then obviously I mean up to an additive epsilon, because we can't get perfect maximization and with high probability. So if you think about the optimal auction for a distribution as a property that you wish to learn, property here is to, the goal here is to pack learn an optimal auction for this distribution from samples. Okay, so let me frame this. Yeah.
So is it, do you allow for the situation, and maybe this isn't exactly relevant,
Mm-hmm.
where the kind of history that you look at is the best prior best distribution on, I mean, it's as if you had a parallel universe and you were able to do this many, many times,
Mm-hmm.
where you get to see the results of auctions
Mm-hmm.
and sort of maximize the distribution that would have given the auction that you actually chose,
Mm-hmm.
maximize the distribution that would have predicted the kind of results of the auction, and sort of kind of implicitly determine what.
I'm not sure I follow. Could you?
Well, you're sort of describing a situation in which you kind of explicitly, either from sampling or
Mm-hmm.
something, describe the distribution.
Yeah.
And then design the auction.
Yeah.
And prove that it
Mm-hmm.
sort of does the
Yeah.
results it can do. What if you can you choose an auction? Maybe it's not optimal,
Mm-hmm.
but make observations that then allow you to say, well, what's the best distribution that would have.
Okay. So for that you need to have some assumption on the distribution space to do something like that.
Yeah, that's true.
And we don't.
This is like parameter free.
Yeah. So this distribution could be anything, and when I say anything, I mean completely anything. We're going to assume that it's bounded and that we know a bound. Otherwise, it's impossible. It can't be proven. But the thing is that this distribution could really be anything. You don't have any assumption. You can't do any kind of maximum likelihood, whatever. But thanks for the question. Okay, so let's frame this question in terms of previous papers. So assume for concreteness, this is almost the most general thing that's known. Variations on this are known as well. That we have one item for sale, and that all values are bounded by some given h. There are works that deal with tails that are nice enough, but let's assume for now that everything is bounded by some given h and that we know it. So Huang et al. 2015, it's actually an older paper, it was published in 2015, solved this. And when I say solved, I meant that they gave a polynomial time algorithm that takes polynomially many samples and outputs an auction that is pack for the unknown distribution. So they solved it for the case of one buyer and what's called a regular distribution. It's a certain assumption on distributions. Whoever here knows some results in the field, it's what's called Meyerson regular, but forget about that. It's some assumption on distributions that is common because it simplifies analyses, but we'd like to avoid that if possible. And then Colin Roughgarden, that was stock 2014, did also regular distributions, but heterogeneous, many buyers, each one with their own distribution. Nikhil Devanur et al. Tightened these bounds. They actually later generalize even further. We'll get to that, but I'm describing the situation as they were at the time that we published our paper. So for arbitrary distributions, that is not necessarily regular. There is, from last year, Tim Ravgarden and Oka Schreifers. They did arbitrary distributions, but IID buyers. Their analysis really crucially depends on the fact that you may have many buyers, but they all have the same underlying distribution. The reason that this is important, we'll get to that later, is that the empirical auction, it's known how to solve this problem when you're given full information about the underlying distribution, and the solution is simpler for regular distributions and simpler for IID bidders. So the fact that special cases are easier comes from the fact that even if you had all of the information, optimizing for a given distribution is easier with these assumptions. So the last case that was left open was heterogeneous buyers, each with their own distribution possibly, and arbitrary distributions. So Jamie Morgenstern and Tim Ravgarden in 2015, they didn't quite solve it, but they showed that information theoretically, polynomially many samples suffice. So they have a very large space of auctions. They show you that polynomially many samples are enough so that if you take from this large space the auction that performs best on the samples, it will approximately maximize revenue on the underlying distribution, but they have no algorithm, no efficient algorithm to traverse that actually infinite space.
What's the best known if you assume you know the distribution?
You mean in terms of complexity of the?
Of algorithm.
It depends on how it's represented, really. Once it's a general distribution that's not given to you as a distribution over samples, it really crucially matters how it's represented to you. I mean, which kind of access you have to it.
What kind of results existed before?
So the results before that are from economists, which say there exists a mechanism and it has the following structure. It wasn't like, here's an efficient way to calculate it. But if the underlying distribution is discrete, then you have things that are polynomial in the support.
In the support, in the support, or
in the sum of the supports.
Okay, so it's pretty efficient.
It's pretty efficient, yeah. So what I'm going to talk to you about today, after this introduction, is closing this gap, giving a polynomial algorithm that takes polynomially many samples from n heterogeneous distributions, any distribution bounded by supported on 0 to h, and outputs an auction that approximately maximizes revenue with high probability. So at this point, I'm guessing that quite a few people in the audience are thinking, okay, you get many samples, take the uniform distribution over the samples. So maybe that means just taking one sample IID with multiplicities, and take that for each buyer, maybe do the product distribution, whatever. And then I just told you that it's well known how to optimize for a given discrete distribution. So do this optimization, get an auction, and well, since it's optimal for this, it will probably be almost optimal for this underlying distribution that we don't know. So the potential problem, as with many learning scenarios, is overfitting. It may be the case that tiny learning errors in learning this reconstructed distribution make us tailor an auction to this reconstructed distribution that would lose non-negligible revenue over the original unknown distribution, the underlying distribution. And the state-of-the-art previous papers, the ones that I talked about, they indeed use the very deep understanding of this process of Bayesian optimization, given full information about the distribution, how to get a revenue maximizing auction for it. That's Meyerson 81, got a Nobel Prize for the other stuff. so they use a very deep understanding of that and tweak it very gently here and there, and then use various other techniques from statistical learning, pseudo-dimension, stuff like that. And it's delicate analysis. Some of it is performed in quantile space, which probably doesn't mean much to people in this room, but it's as far as auction analysis and AGT goes, it's not the simple tools. Let's say that.
Excuse me?
Yeah.
State of the art for what?
State of the art for the special cases, these papers.
Which I can see the laser. So.
Ah, you can see the okay. So I'm talking about all the papers that solve special cases of this problem.
Oh, they use the Myerson paper.
They use the Myerson paper, and they tweak the optimization algorithm of Myerson and tweak the way you reconstruct this from the samples and tweak, etc., in order to make things work. And it's quite a delicate analysis.
So they do follow like the
This, yeah, but with many tweaks. They tweak both how you do this and how you derive the distribution that you start working with. So there are a lot of tweaks.
Do you
Yeah.
know that just doing this thing doesn't work? Or
Okay, no, so that's a good question. So
we can't prove that it does.
yeah, I think it's cool. I mean, from reading the previous papers, it's between the lines. There are some hand-wavy explanations about what could go wrong. To tell you that could actually go wrong with non-negligible probability, I don't know.
There isn't like an example where.
No, there isn't, as far as I know,
But you
at
need
least.
to assume something, I guess, because if it's probability 1 in 10,000, I have a value of 1 billion.
So okay, so that's why we assume that we know a bound on the distribution. We said that there is a bound h, and we know it. Otherwise, yeah, precisely. Okay, so that's a good question that we don't know the answer to. Whether there can really be overfitting, I don't know. All of the literature seems to assume that there can be. I'm not as confident personally, but it's really it's a delicate question, because it's a question of whether this algorithm of Myerson can overfit. So I don't know the answer.
There isn't a black box that would prevent overfitting, like.
Okay, so we're going to talk exactly about that. So our approach is closer in some sense to this naive model. We basically say, take the samples, take the uniform distribution over the samples, change nothing, don't do any kind of tweaks, perform Meyerson's optimization on it as a black box, don't do any tweak, and round the auction when you're done. You meant something like this. So when I say round the auction, I'm actually hiding a lot of stuff in there. I'm going to tell you about that soon. It's something that was not, it's not a technique that existed before that, but this is our approach. And thank you for the question. I didn't invite it, but I couldn't have asked for a better one. We treat everything basically up to this point as a black box. Our analysis is only in a value space. It's a simpler analysis than previous papers. We don't need pseudo dimensions or VC dimensions or whatever. We simply have a union bound that's enough for us. So it simplifies the analysis, and that's it. So the very high level analysis before we jump into the details. We have the underlying distribution that we don't know. We get samples from it. We reconstruct the uniform distribution over the samples. We perform Bayesian optimization to get some auction A that is optimal for the uniform distribution over the samples. And then we round it. We're going to say soon what that means. To get an auction A prime, we're going to reason about why A prime is optimal for the empirical distribution up to epsilon. And then we're going to reason about why A prime is almost as optimal for the original distribution. That's the rounding gives us this robustness of saying that A prime performs similarly well here and here. So it's time to say what rounding means. So we view 0h. I remind you that all of the distributions of all of the buyers are guaranteed to be supported on the interval 0 to h. We view it as being composed of a disjoint union of semi-open epsilon intervals, so 0 to epsilon, epsilon to 2 epsilon, 2 epsilon to 3 epsilon, etc. And we will say that an auction is epsilon if its outcome, so what's the outcome of an auction? An auction is given a profile of bids, one per bidder, and it tells us two things. First of all, who gets the clicker, and second of all, how much they pay. So the outcome is the both the who gets the clicker and how much they pay is constant within each product of epsilon intervals. That's the same as saying that in order to run, the outcome only needs to know the epsilon interval in which each bid lives. So if Mark values the clicker by 2.5 epsilon and Avishai values the clicker by 3 1/3 epsilon, in order to run an epsilon course auction, it's enough for Mark to tell me, well, my valuation is between 2 epsilon and 3 epsilon, and it's enough for Avishai to tell me my valuation is between 3 epsilon and 4 epsilon. We don't need more than that in order to say who gets the clicker and how much they pay. And we will round an auction A to an epsilon course auction A prime using the following process. For each epsilon interval of each bidder, we will choose a value in that interval that we call the representative of that interval. So for Mark, we will have some representative between 0 and epsilon, some other representative between epsilon and 2 epsilon, etc. For Avishai, we will have also representatives. They may be different. And we define the allocation rule of the auction. That's a fancy way of saying who gets the clicker. As follows, we replace, so A prime is an epsilon course auction. So we ask each bidder in which epsilon interval does their valuation lie. And then we treat each bidder as if he bid, we run the original auction and treat each bidder as if he bid the representative from that interval. So say that Mark tells me that his valuation is between 2 epsilon and 3 epsilon. I replace that bid with his representative for that interval between 2 epsilon and 3 epsilon, which may be 2 and 3/4 epsilon, maybe. And same for Avishai, etc. And then I turn to the auction A, and I run the auction A on these bids, these representative bids, and that tells me who wins. Now, I would have liked to also have the auction A tell me how much the person who won paid, but that would not be truthful. That would not be truthful because it opens up the door to slight cheatings, 1 epsilon interval up or down. So what we're going to do instead, and that's, many buttons. And that's a recurring theme. That's not something that we invented. It's a recurring theme in single item auctions. If we say that the winner pays her minimal winning bid, so the minimal winning bid would be the minimal bid that a bidder could have given and still won, then this is guaranteed to be truthful. So in this case, there is maybe Mark versus Avishai. Each of them bids. So since we have defined the allocation rule of A prime that says given bids, who gets the clicker, we can ask given for Avishai, what is the minimum bid of Mark that would get him the clicker? That's well defined since we know for each pair of bids who gets the clicker. So there is a minimal bid, an infimal bid, if you wish, of Mark that would get him the clicker. That's his payment. That's, yeah.
Doesn't that depend though on everybody else's bid?
Yeah, but that's fine because what the auction has to say for a bid, if for every given a profile of bids for everyone, who wins and how much they pay. So, and the fact that you're very correct in your observation. The fact that the payment only depends on the other's bids, it's exactly what makes it truthful. Given everyone else's bids, Mark's choice with his bid is basically win and pay something that he can't control and is already fixed by the others, or not win. He has no incentive to misreport so that he wins and pays less. That's so precisely making it depend only on the other's bids, that's what makes it truthful. It's a very correct observation. Okay, so this is rounding.
Are you selling one item?
One item, yeah, one item. So we're going to reason to first show that we can efficiently find a rounding, find representatives for each epsilon interval of each buyer, and that this rounding does not lose much revenue over the empirical distribution. And then we're going to claim that this actually avoids overfitting. We're going to claim that if we started with polynomially many samples, then that we claim that any rounded optimal auction has, with high probability, almost the same revenue on the empirical and on the real distributions. And at this point, this may sound odd, because I told you that the output of the Bayesian optimization algorithm maybe could overfit because it has a very high dimension. And then I'm telling you, I'm throwing in like more degrees of freedom in the choices of all of the representatives, and then suddenly I get something that can't overfit. And that may sound odd because supposedly I've only increased the dimensionality by throwing in degrees of freedom of how I could choose the representatives. But in fact, something collapses there. We're going to see that while there are many possible outputs to the Bayesian optimization algorithm and many choices of representatives, there aren't as many auctions that are the output of taking an output of the Bayesian optimization algorithm and then rounding them. So for many, many choices of optimal Myersonian auctions, and for many, many choices of representatives, we're going to collapse to the same auction. And this low dimensionality is what's going to give us the no overfitting result. We'll see that soon, but that's the main argument that we're going to use. So before I can better go into the details of that argument, I'm going to have to tell you a little bit about Myerson's optimization algorithm. There's a lot going behind the scenes there. I'm only going to tell you a little bit about how the optimal auction looks like. So the solution is something that we call a Myersonian auction. That's not a general name. It's a name that we use in our paper. So, and it's represented by an n-tuple of functions. By the way, tuple? Who's a native English speaker here? Tuple? Tuple. OK, thanks. So it's an n-tuple of functions, of non-decreasing functions, one per bidder. And these functions are from the bid space of the bidder to the reals, to what we call virtual value space. Well, that's a name that's been around for a while. And these are called the virtual valuation functions of the buyers. And forever, anyone here who knows Myerson's algorithm are actually talking about virtual valuations. If you don't know what I'm talking about, then forget the last sentence. So say that we have two buyers. Each of them has a bid space between 0 and h. And then we have these functions phi1 and phi2 that take us from the bid space to the virtual value space. And in this Myersonian auction, there is a winner unless everyone has a negative virtual valuation. I'm going to use the term virtual valuation to refer also to the output of this function when applied to the bid of the bidder. So if both have negative virtual valuations, negative virtual bids, then there is no winner. Otherwise, the winner is the bidder with the maximum virtual bid. So maybe F1 bids, maybe the first bidder bids B1 and the second bidder bids B2, but maybe the virtual bid of the first bidder is higher. So they will be awarded the item even though they bid less. And once again, to make this truthful, the winner pays her minimal winning bid. As I told you, it's a very old recurring observation that this is basically the only way to make things truthful. So you don't need to know at all how these functions are miraculously calculated. that won't interest us. We don't need to know anything about further restricting how these functions look like. It's enough for us that they are non-decreasing and that the winner is chosen like this. This is all that you need to know about Myers-Brownian auctions. So first, I'm going to do the no overfitting thing, and I'm going to claim to you that any possible rounded Myers-Brownian auction with high probability has almost the same revenue on the and on the true underlying distribution. And the key observation, as I said, we will show that the set of all possible roundings of all possible optimal auctions is small, even though there are many, many very high dimensional optimal auctions and a lot of ways to round them, obviously. So we will claim that a rounded Myers-Brownian auction is always of the following form that we call H epsilon simple. So an auction is H epsilon simple if there exists a sequence of distinct pairs of bidders and epsilon intervals, such that the winner is the first bidder in the order whose bid lies in that epsilon interval. So let's give an example. So here's an example of such a sequence. So the first element of that sequence could be Mark and his highest epsilon interval. The second, if Mark's bid we said that we get arbitrary bids, but we replace a bid in each bid in a certain epsilon interval with a representative bid from that epsilon interval. So the original auction, the original Myers-Brownian auction pre-rounding, will only be run on representatives. Furthermore, we don't even need to know the exact value of each virtual valuation function on each representative. We only need to know their order. So we only need to know if Avishai's virtual valuation function on his representative for the fourth epsilon interval, if that is higher or lower than each of Mark's possible virtual bids, a virtual valuation applied to the bid. So basically, we have, for each bidder, we have H over epsilon representatives, and we need only to know the order between them in order to decide who wins. So there is one of them has a representative with highest virtual value overall. That bidder and the epsilon interval of that representative would be the first element of the sequence. Then there is some representative somewhere, and such that the virtual valuation of the bidder that this representative belongs to gives the second highest virtual value ever among all of these virtual values of all of these representatives. That's going to be the next one in this, etc. At a certain point, virtual valuations on bids become negative. We said that for Myers-Brownian auctions, if everyone has negative virtual valuations, no one gets the item. That's where we stop. So every rounded Myers-Brownian auction looks like this. And since specifying this auction is basically specifying an order on h over epsilon to the n items, values, then the number of distinct h epsilon simple auctions is at most exponential in polynomial in hn and 1 over epsilon. That may seem like a lot, but we're going to soon see that using the right concentration bound, we actually need log of that many samples, then that's fine, and we like that. I think that there are some similarities to previously studied auctions, but I think we're going to skip that for this audience. Okay, so uniform convergence. So what we would have liked to say is lambda, that's the number of h epsilon simple auctions in the world. So there's at most exponential in polynomially many such auctions. So apply your favorite concentration bound here, Azuma, Chernoff-Hofding, whatever. Taking log of that and poly in log of that and poly in log 1 over delta many samples guarantees that each simple auction, each h epsilon simple auction, performs similarly well on the true distribution, on the empirical distribution. I remind you that the revenue of an auction from a distribution is the expected revenue from the distribution. So you can think about the revenue from a given bid profile as a random variable, and we're asking how many samples do we need so that the expected of this random variable on the empirical distribution is close to its expectation on the true distribution. And the answer is we need log as many if we want this to happen with high probability over all simple auctions, then we need log of the number of simple auctions many samples, and log of 1 over delta, obviously, also. Yeah. Okay, so think about RA, that's the revenue, RA prime, that's the revenue from the auction A prime, as a function from bids to my revenue from these bids, to the payment that I get. The expected revenue that I get from the auction A prime is the expectation over the maybe empirical distribution or true distribution of this random variable. So in order to guarantee that for each simple auction I get similar revenue on the empirical distribution and on the original distribution, I basically have to ask myself a concentration question. How many samples do I need such that the empirical average of this random variable is close to the theoretical expectation?
So like you're actually sampling RA by sampling the B's? And then
Yeah.
Okay.
Okay, so what I said now is almost correct. You're right that something bothered you. The problem is that doing this kind of bound says that the empirical expectation over the tuples that I sampled is close to what happens in the underlying distribution. But Meyerson's algorithm doesn't help me to maximize the expectation over the tuples that I sampled. Meyerson's algorithm can only help me maximize my expectation over the Cartesian product of the samples from each of the distributions. Maximizing the over the tuples, which basically corresponds to revenue maximization when the bidders are correlated, is a hell of a lot harder. So we would like to guarantee that the revenue, when we evaluate it on the Cartesian product of the samples, is close to the revenue on the underlying distribution. For that, Chernoff-Hofding or Azuma or whatever is not enough. Luckily, we thought we actually proved a new concentration bound here. Then we realized that Nikhil-Devanur et al. Proved it last year. And then we realized that actually Babichenko et al. Proved it 2 years before that. So it's quite a useful concentration bound. And it gives exactly this. It says that even if what you want to be close to the underlying expectation is the expectation on the Cartesian product of samples versus on the tuples of samples, still log of whatever suffices in a similar way. There's a bit of a difference in constants, etc., but qualitatively it's still log, and that's what we need. So we apply this and no overfitting. And what I still have to tell you is how we choose the representatives. How are we with time? Okay. So it basically boils down. So our algorithm will be this. We perform Bayesian optimization. We somehow round without losing much revenue. The result is an H epsilon simple auction. We began with enough samples to guarantee that whichever H epsilon simple auction is output here, it's going to perform similarly well on the empirical and on the true distribution end of argument. So what I still owe you is to explain to you how I find these representatives in a way that does not lose much revenue, and how do I do that efficiently. So this lemma, let's state it to be sure that we're all on the same page about what still has to be proven. There exists an efficient deterministic algorithm that for input 1, a product distribution where each f hat 1 through f hat n is uniform over a multi-set of t-sampled values. So this is the empirical distribution, the Cartesian product of distributions. And the other input is the auction that is optimal for this empirical distribution. And as I said, it's long been known that this A can be found from this empirical distribution efficiently. And given this input, it outputs an epsilon coarse auction A prime, that is an epsilon rounding of A, and whose revenue from this empirical Cartesian product is less than an additive n epsilon smaller than that of A. So we may lose up to an additive n epsilon in revenue due to rounding, and that's fine. Actually, a nice side effect that we have, and the proof is going to be completely the same, we'll see that soon, is for every product distribution whatsoever, now forget about the fact that it comes from a discrete sample distribution, we need that for efficiency, not for existence. Whichever product distribution you give me and whichever auction you give me doesn't have to be Myersonian, that also we will need for efficiency later. I can give you an epsilon coarse rounding of A, an epsilon coarse A prime, whose revenue from this distribution is less than an additive epsilon smaller than that of A. So the possibility of rounding does not depend on the on these distributions being empirical distributions. They can be arbitrarily complex distributions. Does not depend on this auction being a Myersonian auction. This is a new result that was not known, and we prove it, that you can always do epsilon rounding non-constructively without losing much. The additional assumptions here that each of the f's are uniform over a multi-set of t-sampled values, and that A is a Myersonian auction because it's optimal for the empirical distributions, that's needed for the efficiency of the algorithm. But if you don't need the efficiency, then we can show even this. And this, as far as I know, it's not been known before that there exists a finite set of auctions such that for any distribution that you want, you can always round to one of them with epsilon loss. So that's of independent interest. And this less than additive epsilon is actually tight. You can't guarantee more than that when you round. Here we lose an additive times epsilon because we need an efficient algorithm. We don't know whether that's tight. Maybe the n can be dropped here. I don't know. Could be an interesting question. So in order to explain to you how we do either of these, I'm going to ask you to think a bit differently about Myersonian auctions. This is not new. What I'm going to tell you now has been known for a long time. instead of thinking about applying the virtual transformation to each of the bids and then checking who wins, I'm going to ask you to think about each bidder as having a reserve price that is set for bidders. That relates to what you said earlier. So take the bid of bidder 1, apply his virtual value transformation to it, apply the inverse of bidder 2's virtual valuation transformation to it. You get something in bidder 2's bid space. If he bids above it, he wins. If he bids below it, he loses. We're going to call this the reserve price for the second bidder. Just to completely not lie to you, if the virtual value is of the first bidder is below 0, then the reserve price is what we get from applying the inverse transformation of bidder 2 to 0. Because we said that if bidder 2 has virtual value below 0, then no one gets the item. So just to be like completely, but I'm not lying to you now. That's it. There's nothing more complicated here. So the problem is, once you think about my reserve prices being set up by everyone else, the challenge in rounding without losing much is that you can, if you round my intervals, you can quite easily find representatives in a way that you lose less than epsilon revenue from me. So you charge me a bit less. You choose the representatives in a way that charges me a bit less for everything, but it's only epsilon less, and then there are representatives that do that, and everything's fine. The problem is that by doing that, you affect the reserve price that I induce on other bidders, and that can be that could be completely chaotic, in a sense that by rounding my bid down even a little bit, you may be lowering the reserve price that I induce over Avishai and Mark by a lot, really a lot. This happens because we don't know that the inverse of phi 2 in this case is nice in any way, or Lipschitz or whatever.
But it is bounded.
It is bounded, but it's bounded by maybe the reserve. So maybe the reserve price that I induce on you drops by as much as capital H. And if the auction results with you winning, you're gonna pay capital H less. That's much more than epsilon less. That's the problem. And in fact, we show that it is due to this reason, we show with a concrete constructed example, talking about your previous question, that it is impossible to obtain negligible loss overall by any method of distribution oblivious rounding. What do I mean by distribution oblivious? Take any rounding rule, any choice of representative rule that does not take into account the empirical distribution over which we want to lose not much. There is going to be some distribution for which this rounding rule loses a lot. So you can think about taking the minimum representative from each epsilon interval, the maximum representative from each epsilon interval, etc. None of that is going to work. None of even more complicated things are not going to work. I know that I have only, okay, still have time. That clock is frightening. Yeah. Okay. So our main, so this can't be done. Somehow we have to choose the representatives in a way that's dependent on the distribution for which we wish to not lose a lot of revenue, and we need to do that in a way that doesn't somehow affect. It doesn't change our overall effect on the reserve prices that we set for others. So here's a non-constructive way to do that. We're going to turn that into a constructive way soon. The main idea is to choose the representative randomly. So we're going to have a randomized auction with randomized choice of representatives. We're going to make that, we're going to de-randomize it soon. But for now, think about choosing the representative for bidder i's interval j randomly according to the distribution of that bidder's empirical according to the empirical distribution of that bidder, restricted to that interval. So essentially what we do is we resample bidder i's representative. Since it's a coarse auction, I ask Mark where his bid lies. He only tells me between 4 epsilon and 5 epsilon. Could be anything there. And I say, okay, I don't know what that is. I'm going to resample his bid from that interval so that it behaves as if, overall in expectation, probability, whatever, as if Mark told me his real bid. So the distribution of reserve prices that Mark induces onto the other bidders is exactly the same as if he actually would have told me his real bid. If we take the expectation, the distribution of the reserve price that Mark induces over other bidders, conditioned on the fact that his bid is somewhere in that interval, it's precisely the same distribution as saying, throw away Mark's bid from that interval, redraw something from the same distribution from that interval, use that to induce a reserve price onto the other bidders. So that observation, and that observation tells us that there is no effect on the distribution of the reserve prices induced on the other bidders. I still will have to show you, we'll do that a bit slowly slower in the next slide. I will still need to show that there is negligible loss from this randomized choice of representatives from the revenue from Mark. But we've solved the fact of the main problem that I told you about, that the choice of representative for Mark might violently affect the reserve prices set on others. So once you believe me that I can do that, we'll do that in the next slide precisely. The argument will be, okay, so there is negligible, so we find a way to randomly choose representatives so that our expected revenue loses at most epsilon. That means that there is something in the support of that random choice, something deterministic, that loses no more than epsilon. That's like a standard something is higher than the expectation argument, probabilistic method argument. So if there is, to go again, choosing a random choice for each representative is basically a random choice of the rounding overall. If an expectation over this rounding we lose no more than an epsilon, then there is something deterministic in the distribution, in that distribution, some deterministic way to round that loses no more than epsilon. And our efficient algorithm for doing that will be basically round interval by interval, do the optimal local greedy choice for each interval before going to the rest, and that's going to be fine as well. That would make us lose an additional n factor, n epsilon versus epsilon, but that would work. For that to work, we would need, the reason that I told you that we make two assumptions in this higher lemma. First of all, that everything is discrete, and second of all, that A is Myersonian. In order to do this thing of finding the best representative for each interval and moving on, to know that we found the best representative, we need a way to evaluate the expected revenue given a specific choice of a representative. So for a general auction, evaluating the expected revenue of that auction, we show that to be we show that to be NP hard. But for Myersonian auctions, we have an algorithm to do that. So that's the last building block. Another way to go about doing that, and that's like actually a general learning thing that we haven't seen anywhere else. So a random way to use this result that says that randomly, if we choose randomly, we don't lose a lot of revenue and expectation, would be, okay, if by random choice you don't lose a lot of expectation, then randomize for polynomially many times. One of them will not lose a lot of revenue with high probability. Take that one. Take that choice for representatives. That would have actually worked as well. But that results in a randomized rather than a deterministic algorithm, a randomized learning algorithm rather than a deterministic learning algorithm. And we actually have a pretty cool way of de-randomizing that. using the randomness from the samples that we have sampled. So earlier we got a lot of samples that make up the empirical distribution. From each pair of samples, of consecutive samples from the same distribution, if they're different, we get a bit, a truly random bit, but according to whether the first or the second one is higher, because they could have come at any order. We can use these random bits to de-randomize this process. Now you're going to ask, well, maybe you don't have too many pairs of samples that are different. Maybe you have many pairs that are the same, and therefore you don't get a lot of random bits from here. In that specific case, our algorithm, this algorithm of choosing many representatives over and over again doesn't need a lot of random bits at all. Because it means that the empirical distributions don't have a lot of entropy. So randomizing from them doesn't need a lot of bits. So we actually show that this whole thing ties together. And that actually could be useful in other learning situations. The fact that the difference between deterministic learning algorithm and a randomized learning algorithm is not that far away if you have enough randomness coming from your input. So that's an observation that we actually use. As I told you, we have an efficient greedy algorithm, but once we go beyond single item, I'm not going to have time to get to that, but we have results beyond a single item, then we actually only know how to do this de-randomization of the random algorithm. The deterministic greedy doesn't work anymore. How are we with time? Okay, so we're pretty much done. Do I have 4 more minutes to do the core of the argument with you and then finish? I don't know. How?
Yeah, we're doing very well on time. Yeah.
Oh, okay. So the core of the argument is as follows. Fix a profile of bids for everyone else except for Mark. We're going to round epsilon interval j of Mark, and we're going to claim that, by round I mean randomly round, we're going to replace Mark's bid, whatever it will be.
I'm sorry, what is a profile of bids?
A profile of bids is simply a bid for each bidder.
A fixed bid?
A fixed bid. Fix a profile of bids for everyone except for Mark. Now we're going to round, given some auction, we're going to round Mark's epsilon interval j in that auction, which means that instead of the auction will become epsilon course on that interval. Instead of asking Mark for his bid, we're going just to ask him for his if that bid lies in that interval, we're going to throw it away and replace it with a randomized bid that's resampled from the same distribution and adjust so that he pays his minimal winning bid. And we're going to claim that this does not lose much, and it will basically, this is the building block of everything that I've shown you so far. So let's start with the easy part regarding the revenue from other bidders. So if Mark's bid is not in epsilon interval j, this is like the silliest case, then the revenue from any of the other bidders is unaffected, right? Because Mark's bid is not in epsilon interval j, so we replace it. We don't replace it. We continue with it. So the bid profile, including Mark's bid, is unchanged. So the winner is unchanged. And if the winner is not Mark, then that winner pays his minimal winning bid, which is the same. Okay? So far? Yes? No? Again? Ask me some question? Okay. And so what happens if Mark's bid is in epsilon interval j? We claim that in expectation over all of the bids of Mark from epsilon interval j, the revenue from any other bidder is unchanged as well, right? Because if we take in expectation over all of Mark's bid in that epsilon interval, and we either, to determine the revenue from another bidder, we either use Mark's or Mark's resampled bid. It has the exact same distribution, so the revenue from another bidder would be the same. What happens with the revenue from Mark? So now we're going to reason not about whether Mark's bid is in the rounded interval, but rather about whether his minimal winning bid is in the rounded interval. So if the minimal winning bid of Mark is not in epsilon interval j, then I claim that neither the outcome nor his payment is affected. Why? Because if his minimal winning bid is not in the epsilon interval that we rounded, then any bid that used to win still wins. Any bid that didn't win still doesn't win. His minimal winning bid is unchanged. If he bids anything below this, before and after, say that this is a minimal winning bid and that we round this epsilon interval. Anything below this loses. Anything above this wins. This reshuffling that we have here doesn't matter because any of these bids would have won. Any of these bids still wins. So the probability that Mark wins remains the same. And it remains the same because it's his minimal winning bid. Same if we round this interval. Anything below this minimal winning bid doesn't win. Doesn't matter whether that we shuffle things around here. And if he wins, it's the same payment. So the last thing that's interesting is what happens if Mark's minimal winning bid lies in the epsilon interval that we're reshuffling. We claim that his winning probability, once again, over all of the bids in this epsilon interval is unchanged. In the sense that if you take a bid of Mark conditioned on the fact that it's in this interval, he has a certain probability of winning. If you throw that bid away and replace it with a resampled representative, the resampled representative has the same probability of winning. The only difference is going to be with the payment of Mark. Maybe his minimal winning bid shifted up to the minimum of that interval. Because maybe due to the resampling, maybe that caused any bid in this interval to win. So his minimal winning bid for a certain realization may have dropped from here to here. So he pays us at most epsilon less, no more than epsilon less. So this together tells us that if his minimal winning bid is in epsilon interval j, his winning probability is unchanged. If he wins, he pays something that's at most epsilon less. So overall, if his minimal winning probability here, he pays us, we get epsilon less from him if he wins. And recall that if his minimal winning bid is not in the epsilon interval that we rounded, then we lose nothing. So for each fixed profile of bids for the others, revenue is lost only when we round the specific epsilon interval where Mark's minimal winning bid lies. Rounding of all of the other epsilon intervals we get for free.
I don't see why the payment changes actually.
Why the payment changes? Because once you pick okay, so say that the representative that you picked was here. It was a winning representative. So now any bid in this interval wins because they're all replaced with a representative that wins. So the new minimal winning bid is the minimum of this interval because anything in this interval wins. So the minimum bid in this interval wins as well. So that's his new minimal winning bid. That's what he pays. So that's the only thing we lose revenue for. So for each profile of bids for the others, if we round all of Mark's epsilon intervals, we will only lose revenue when we round the specific epsilon interval that contains his minimal winning bid. We'll lose, overall, we will lose less than epsilon times his winning probability. And when we round the intervals of the others, we won't lose anything from Mark. So for each bidder, we lose at most epsilon times his winning probability. When you sum everything up, you lose at most epsilon. If you wish, epsilon times the probability that there is a winner. When we do this one by one, we have to be like the greedy rounding of rounding interval by interval instead of rounding with randomized, each time rounding to the best deterministic one, then I can't tell you that we lose overall epsilon, we may lose overall epsilon for each bidder because the rounding that we do to Mark's values changes overall his winning probability, changes other people's winning probability. I can no longer say that the sum of all winning probabilities is 1. We can bound it by n. That's so we have some. Okay, so the main result is a polynomial time algorithm that takes polynomially many samples and does what we want it to do. We have some extensions to other what's called single parameter environments where there could be more than one bidder, like maybe 5 winners who win identical copies of the clicker or stuff like that. Maybe some other more general. We actually generalize even beyond things that were known by the previous papers for the special cases that I talked about earlier. And that's basically what I had to say. Okay. So thank you very much.